All right. Well, I think we're to the main event. Let's talk about the many core beasts from AMD, and there they are. Chris took a look at these. He actually has had screaming servers, or has screaming servers still in his lab. AMD
Yes, not
Bergamo.
screaming currently, but yes, like 90 decibels each.
Yeah, there you go. AMD Bergamo and GenoaX Performance Review Epic chips for big iron workloads. That is the title of Chris's extraordinary deep dive into the performance of these server chips. Chris, I mean, 128 cores, get out of town. 3D V cache on the GenoaX. I mean, serious business.
So I really want to cover how they got to 128 cores on one of these chips, but I think it makes more sense to start with the GenoaX breakdown because it is something that they have done before. We had Milan in the third generation, and then Milan X with 3D V cache added on top. So that's basically giving high performance compute workloads a lot more on chip memory to work with so that they can keep their workloads closer to the compute and basically burn through particular workloads very, very well. One thing you will find that hopefully is a good sign for that mobile X3D chip we just discussed is when you look at the specs between the 9684X I have here with 96 cores and the 9654, which is the regular Genoa chip without 3D V cache and 96 cores. As you look across the specs, you find the default TDP 400 watts for both, 320 to 400 watts configurable TDP range, but more impressively, the clock speed ratings are actually about the same. I think it's 2.5 on Genoa versus 2.55 for your base clock on Genoa X, going up to 3.7 as your max boost. So at least on paper, you're not giving up any clock frequency to go with the 3D V cache part. Now, there are some asterisks that because when you have more cache on the chip, it's going to be consuming more power just to run the memory. So there's still some consideration. And as we get into the benchmarks, you'll see that. But yeah, basically the Genoa X parts are Genoa with that layer of 3D V cache stapled on top to give them 1.1 gigabytes of cache on the processor, which is awesome.
Yeah, man.
Can I interrupt you? I don't want to mess up your flow. Can I interrupt for one quick second?
Go.
So when we were getting briefed on this, I was out at AMD's event when they were showing it off, and something that gets lost, and like it's kind of tough to show in benchmarks, right? Because we have limited time and to pull this off. But some of AMD's clients with these 3D V cache Epic chips, you see better than linear scaling with the Genoa X, because at some point that cache pool becomes so big that customers, even big data customers, it fits on the CPU all the time, and performance just skyrockets. So it's such an insane amount of cache. It's just wild. I just wanted to throw that data point in there.
Now imagine this with something like the Intel Xeon Max approach that puts HBM on the on the package as well, and then things would really fly. But we can wish for the future. So yeah, that's Genoa X. It's awesome, high performance compute oriented. Bergamo is a very different approach. So it's still that Zen 4 at its heart. Very similar structure. You're still getting the central IO die flanked by the different CCDs. But the CCDs themselves are different. So these are using the Zen 4C architecture, which takes the Zen 4 layout and compresses it down in area by like 40%. I think I've got the number here somewhere. So basically much smaller physical footprint so that they can actually put 16 cores instead of just 8 on a single CCD chip. There are some concessions with that. Mainly you get half the level 3 cache of Genoa per core. And you get lower clock speeds as well because everything is because everything's closer together. They can't run the clocks as fast without it kind of getting some. It affects how much frequency they can push through the literal circuits of the chip. So you have some considerations with that, and also the through silicon vias that enable 3D V-cache to be put on top of the chip is removed as well. So we're not going to see a 3D V-cache version of the Zen 4C chips. But you get a lot of cores with this. So with GenoaX, you get up to 12 CCDs on the package to give you the 96 cores.
Mhm.
Bergamo is 8 CCDs, but because there's 16 cores, that gives you 128 cores per chip, 256 threads, which is just a lot. Yeah, you are losing cache, you are losing clock speeds, but for web first cloud type workloads where density is king, they don't necessarily care about the reduced cache. They don't necessarily care about the lower clock speeds. They're going to benefit in that scale from density. So
Yeah.
these are much more, both the GenoaX and Bergamo are very purpose built chips for particular customers. They're not big markets, of course. But if you're just looking for a web server to, or just a regular server to run whatever workloads, Genoa is still probably going to be your go-to. As we'll get
Yeah.
into the benchmarks, but
Yeah. Well, what occurs to me is that, as you said, Chris, purpose built, right? So, what occurs to me is that the two main players here, Intel and AMD, and there's certainly others coming into the market these days, Ampere, and the likes of TensorTorrent and things like that. Pretty cool stuff.
Mhm.
But when it comes to the way they approach the market, Intel and AMD, Intel went with this accelerator approach for Sapphire Rapids. It's specialized as well. It sort of caters to certain workloads, whether it be, I don't know, web compression technology or IPsec acceleration, things like that. Whereas AMD took a different approach where they have a purpose-built core architecture and or memory structure in the case of
Right.
GenoaX, to address different markets. And that's what I think what's interesting, and the nuance of the benchmarks that you're going to get to next is that you'll see GenoaX has a very specific market, data science and other markets that have these large workloads that can fit in that cache and benefit from that, more than linear scaling that Marco talked about. And then our Bergamo, where, yeah, as you said, Chris, cloud native core density per socket is king. The more physical cores we can get and the more threads we can get on a chip, the better, for just general purpose compute in the cloud. So, yeah, cool stuff. And it's interesting the way the two juggernauts are going at it differently. But I'm sorry,
Yes.
why don't you go ahead and dive in there, Chris?
Yeah. So 2 socket systems we're testing here, which gives you, so GenoaX, that gives you up to
Look at that thing.
384 threads. With Bergamo, that's 512 threads in the system. Like, just
Crazy.
absolutely nutty. This is outfitted with 1.5 terabytes of RAM. I think the Intel system has a terabyte. I forget. I'd have to go back and check. Plenty for the workloads I'm running in any case. So here we have CoreMark, which is just a really quick and dirty compute potential assessment of the chips. And so you see that 128 core, really 512 thread configuration just way out in front. Huge
Yeah, man.
amounts of potential there, as long as the cache isn't stressed. We see the GenoaX chip slightly trail the Genoa chip. So even though they are clock for clock on paper the same, you are in pure compute situations losing out just a little bit through most workloads. So Genoa can still have its edge there. So this is where we kind of get our first taste of the 3D V cache. So the decompression workload is basically per compute to decompress. But as you're compressing in 7-zip, it really stresses the cache of the chips a lot. And so that's where you see the GenoaX chip in the yellow bar come just ahead of the regular Genoa. Little bit of a lead there, but we're going to see better. So Linux kernel compilation, no real surprises here other than you start to see the cache stress and the Bergamo chip fall off despite its higher core count. So lower is better here. But at the same time, the 64 core Epic Genoa part is our current leader by a hair, not a huge difference between the chips. Moving to a larger build of the Linux kernel, we kind of see the same striation. Not too much new there. DeCapo benchmark is it's for I think an interpreter for Python developers who want to write for Java, basically. Very small workloads ultimately, so we're seeing these big chips fall off in performance. It favors the 32 core lighter core stuff. Yeah, Blender here we see Bergamo again, sheer compute. It's taking the lead, and we're seeing GenoaX lose a little bit to Genoa. But I want to get down to, I'm looking for, so we have SQL, nothing too revolutionary there. Both these chips kind of fall off again relative to the mainstream Genoa. So if you're running, PostgreSQL database, just regular Genoa is probably where you want to be. The web server, so I should caution these Apache and Nginx benchmarks through the Phoronix test suite that we use for testing don't necessarily scale to the whole chip perfectly well. So you're going to see some very compressed scaling here. Typically, these workloads would be run many, many times on a particular server like this rather than one monolithic installation. So maybe not the best look at situations, but here we can see this is an approach where the Intel Xeons with their accelerators are able to pull ahead of the EPYC chips. So that it's kind of, you'll see a lot of dominance with the AMD chips, but the Intel processors still have those places with their accelerators where they can punch back and see some significant gains. We'll see in AI in a bit, or with hashing here with the Y-hash, again, has Intel up top because they have those fixed function accelerators that are really, really good at that and very efficient. So now we can get into, just those pin counts on these chips.
Yeah, I know. It's nuts.
So many pins. So some AI workloads with TensorFlow. VGG16 is pretty CPU friendly, scores well with cores. That's not the case with the other TensorFlow workflows. So AlexNet, GoogleNet, and ResNet 50. These chips just aren't performing great for them. They're not built for AI workloads in the same way that Genoa or the Xeon with the fixed function accelerators are. But when you have an AI workload like DeepSparse from Neural Magic, which is pruned down and purpose-built to run on CPUs, they do very well. We see Bergamo, again, way out in front, almost 100 items per second in the async workload ahead of Genoa. And in the synchronous...
Chris, I'm sorry, in a couple of the tests where GenoaX kind of significantly trails original Genoa, is that just strictly clock?
Yeah, it's hard to say exactly because when they settle the ultimate clock speeds, they both settle right around 3.1 gigahertz all core from what I was monitoring. But I think that the GenoaX is clocking down a little bit sooner.
Gotcha.
And I haven't necessarily gotten the resolution to say for certain. Having power go to the cache that's not being used for particular workloads could also be part of the equation.
Gotcha.
But here, so moving to the synchronous DeepSparse, you are stressing that cache, and we see GenoaX come out way ahead of the Genoa part, while the cache-strapped Bergamo chip falls down. So it's you get much more into a workload versus workload. These chips are less consistent because they're built for specific workloads. If you're not running the workloads that they're going to fly in, they're not the chips to buy, and it's kind of that simple. So convolution, 1DNN, these chips don't do that well. The training and inference workloads, similarly, not great. It just takes them a lot longer than 32 core chips. Not built for this workload. That's fine. You just need to know it. Embreeze, this is a path tracing benchmark. And we see both chips actually ahead of Genoa by quite a bit. So this one is stressing the cache, but it also cares a lot about cores. So it's kind of a place where Bergamo can still perform well, but GenoaX is also going to be doing great work for you relative to Genoa. The Pavre,
Good old Pavre.
yeah, Pavre, we see GenoaX virtually identical. That's a margin of error kind of score, but you are losing out with the 128 core parts just by a little bit. Not bad. It's not a bad result, but in terms of your scaling and if you're really min-maxing your optimizations, it's not the chip for that. But if you
Pavre.
occasionally need to run a Pavre workload, you can.
Rendering is on the CPU. Yep.
Yeah. Intel Open Image Denoise. So this is taking, particularly when you have a ray tracing to generate an image and you get a lot of noise in there as a result, and you need to run a denoising algorithm to get a usable image out of it. It's used a lot in cinema, for animated films and the like. Very important workload. And you can see those cores in Bergamo, take the lead for that, even outpacing Intel chips. And this is Intel's own workload. So very impressive there. This is where we really get into GenoaX's stride. So this is the Australian Square Kilometer Array Pathfinder. So taking huge radio telescope data sets, and then it's performing convolutional resampling on the signals that it's getting to basically do the processing to get something usable for the researchers to use. And this is like a 40 or 50% uplift over Genoa just by adding the 3D V cache. So this is the case where you look at this and it just makes sense, because you're working with these massive data sets. It's going into cache, and the 3D V cache parts are just awesome for that. Monte Carlo simulations, on the other hand, while very, very common in physics research and financial simulations and all of that, it's built on very small samples, so not stressing the cache so much. It's something where having a higher clock core in the 32, 64 core parts is just better. So it's kind of it's fun to see these different workloads and how they respond differently to different chips. And ultimately, that's why having all these different options for your silicon are so important. And do your homework to find out which workloads you're running and what works with them well.
Yeah.
The other place for GenoaX is OpenFOAM. So this is fluid dynamics. This first one's looking at the aerodynamics of a motorbike. This is a basic mesh time, figuring out the mesh of the motorcycle, like the actual shape and stuff. Not necessarily what we're interested in, but when it comes to the execution time of actually performing that fluid simulation, we see the GenoaX come up here. Surprisingly, the 32 core actually does very well. Little surprising, but we do see an advantage here. But this is a very small model. This is one that you could run on a desktop processor and get a reasonable result on. Moving up to the driver fastback model, particularly the large version of it, it gets a lot more intense. So again, the mesh in the first result, not as interested in those, taking 667 seconds to figure out, about 10, 11 minutes. But when you actually run to do that fluid dynamics, we see GenoaX way faster. This is saving you hours and hours and hours if you're doing this day in, day out. Huge positive result for the GenoaX here. So it's all looking at how you can leverage these chips the right way and what makes sense for your particular workloads.
Yeah, and again, just to reiterate it, obviously GenoaX, if we were to sort of encapsulate everything here, GenoaX for big data analytics, scientific workloads, things like that, probably a good fit. And then Bergamo, again, if you need to scale to an obscene number of cores to handle as many containers or whatever, additional users per server. If your data center is, totally optimized on compute footprint per square inch or something like that, that's where that thing will fit best. Marco, you've been quiet. We haven't let you speak, and we should, and then we should wrap this baby up.
Yeah, no, Chris did a great. I love this review. Chris did an awesome job, and I love seeing the crazy horsepower out of these chips. And really, for AMD, it's all about offering choice for their customers to maximize the performance for their given workload. You have the Bergamo for cloud native, you have Genoa for mixed use cases, and you have GenoaX for massive data sets. It's all good stuff. And the fact that you can just swap the CPUs into the same platform, AMD is doing a lot of good stuff here.
Yeah. It was in some ways hard to write this review because it was just, okay, it does what it says on the tin.
Yep.
It's that simple.
Yeah. And it's very specific, and it's nuanced. And that's the thing to take away from this, is that there are lots of different types of workloads in the cloud. If you're looking at pure AI acceleration, well, a GPU, from NVIDIA or AMD in that case, certainly, or Intel, would be the right tool for the job. But when it comes to some of these pure CPU server workloads for whether it be cloud or data science, acceleration, then you can actually tune the core and the architecture to address that. And that's what these do. Good stuff from AMD.